In the previous video, we said more CDR bandwidth helps the receiver follow the moving eye. So the natural question is, why not make the CDR bandwidth as high as possible? At first, this sounds reasonable. If the CDR can follow the input faster, shouldn't the receiver become better? But the answer is no. The CDR has two jobs. First, it must track useful timing movement. Second, it must reject harmful timing noise. If the bandwidth is too low, the clock cannot follow the real movement. If the bandwidth is too high, the clock follows noise. So the goal is not maximum bandwidth. The goal is the right bandwidth. If the edge is early, it moves the clock one way. If the edge is late, it moves the clock the other way. But the CDR does not know why the edge moved. Maybe the edge moved because of a real clock drift. This is a useful information. But maybe the edge moved because of random noise. Maybe it moved because of ISI. Maybe it moved because of a crosstalk. Maybe it moved because of a duty cycle distortion. Maybe it moved because the previous bits changed the edge shape. If a CDR bandwidth is too high, the loop responds to all of these effects. Then the CDR is not only tracking TX clock movement, it's tracing noise and distortion. So the key concept is jitter transfer. For input data jitter, the CDR behaves like a low-pass tracking loop. Inside the CDR bandwidth, input timing movement transfers to the recovery clock. Outside the bandwidth, the CDR does not track it as much. This is good when the input movement is slow and useful, but it's bad when the input movement is high-frequency noise. If the bandwidth is too wide, more input jitter appears on the recovery clock. Then the sampler is using a clock that shakes. So higher bandwidth gives better tracking, but also higher jitter transfer. This is the first major reason we cannot just increase bandwidth forever. What does that mean? If you have a limited bandwidth, think about the low-pass filter image for 5 seconds. Bingo! A narrow CDR bandwidth can be good because it filters high-frequency timing noise. For example, random jitter, high-frequency, transmitter phase noise, crosstalk, data-dependent jitter, and residual ISI-induced edge movement. These are usually not timing components we want to follow. If the loop ignores them, the recovery clock stays cleaner. If the loop follows them, the sampling clock moves around and horizontal margin becomes worse. This is the key trade-off. A wide CDR follows more. A narrow CDR feels more. Good design means choosing what should be followed and what should be filtered. What if the bandwidth of the CDR is too much? Imagine the equalized eye has noisy edge. Every transition is slightly different. Some edges are early, some edges are late. If the CDR is too fast, it tries to correct after every noisy edge. Now, the sampling clock is no longer stable. It moves left-right with the edge noise. Sometimes the sample is closer to the left edge. Sometimes it's closer to the right edge. So even though the CDR is fast, the timing margin can get worse. This is an intuitive lesson. A faster CDR can cross the eye if it's chasing the wrong timing information. Then what could be worse than that? Think about the binary image for 5 seconds. Right. Now let's talk about band-band CDR. A band-band phase detector only stays early or late. It does not tell the exact size of the phase error. Because of this binary decision, even in luck, the loop does not seek perfect still. It tends to dithering around the correct sampling point. This is the limit cycle behavior or hunting. That hunting creates the intrinsic clock jitter. This is often called jitter generation over the hunting jitter. If we increase the proportional gain over fixed step size, the loop can track faster. That helps straight out, but the same large step also increases hunting jitter. So band CDR has a natural trade-off. Bigger step helps tracking. Smaller step gives a quieter clock. This is one of the most important reasons. Maximal bandwidth is not the answer. Then let's look at CDR output jitter in detail. There are two different output jitter problems. First, input jitter passes through the CDR to the recovery clock. That is jitter transfer. Second, the CDR generates its own jitter even with a clean input. That is jitter generation. Band hunting is one source of a jitter generation. This means you can tune the loop to pass straight out but still fail recovery clock jitter. You may improve the tolerance mask but increase jitter generation. So CDR bandwidth is now one-dimensional. You need to check jitter tolerance, jitter transfer, jitter generation, and be always together. What's more to check in terms of a jitter transfer? Think about the jitter peaking image for 5 seconds. Correct. A real CDR loop is not an ideal filter. Near the loop bandwidth, the jitter transfer response can peak. That means some input jitter near the corner frequency can be amplified. This is dangerous because the receiver may look good at low frequency and high frequency, but have a weak spot around the loop bandwidth. This is even worse in retimers over cascaded link. If one CDR has 0.5 dB peaking, it may not look so bad. But if 3 similar stages are cascaded, peaking can accumulate. That is why retimer and repeaters care so much about jitter transfer, not only jitter times. Higher bandwidth without enough damping can create more system-level jitter problem. What else could limit the maximal bandwidth or create more peaking and stability issue? Think about the delay image for 5 seconds. Bingo, latency. Modern digital CDR often have significant loop latency. The input goes through sampler or ADCs, then through DSP over equalizer logic, then facilitator, then the loop filter, then the phase interpreter or DCO update. Then the result come back to the sampler. This feedback path takes time. Delay creates phase lag. As CDR bandwidth increases, the delay becomes more dangerous. The loop correction arrives too late. Then the loop can show more jitter peaking, poor damping, or even instability. So the maximal unstable bandwidth is limited by the loop latency. This is usually important in ADC-based and DSP-based service, where the processing path is deeply pipelined. Then, are there other RX blocks that may interfere with the CDR? Bingo! The CDR does not work alone. It works together with the CQE, VGA, DFE, FFE, and sometimes DSP equalization. In a low C channel, edge timing is not clean. Edges are shifted by residual ISI. Different patterns create different edge location. If the CDR bandwidth is too high, it may chase this ISI-induced edge shift, but the equalizer may still be adapting to remove the ISI. So the CDR can fight the equalizer. In Bowery, and Muller receivers. The timing loop and equalizer often share relative samples and adapt at the same time. So the loop bandwidth must be coordinated. The CDR should not so fast that it checks the distortion the equalizer is trying to remove. In many receivers, the data sample can look good while the edge sample is still distorted. This is important. The DFE may open the data eye, but if the CDR uses edge samples and those edge samples are still affected by eyesight, then the CDR phase decision is biased. If we increase CDR bandwidth in this situation, we are making the loop respond fast to bad edge information. That can make the recovery clock worse. That is why edge equalization, edge DFE, over careful timing detector design matter. A high bandwidth CDR is only good if the timing information is trustworthy. Bad timing information plus high loop gain is a dangerous combination. For timing information, think about the transition the image for 5 seconds. Bingo, the CDR needs transition to measure timing. During long run or identical bits, there are no edges. The phase detector has no new timing information. Different CDR handles this differently. Some hold previous decision. Some high-stay the charge pump. Some freeze the update. But in all cases, transition density affects loop behavior. If there are too many missing transitions, the effective bandwidth drops. The loop can drift. The loop filter voltage can droop. The VCO can move away from the lock frequency. If we make the loop too aggressive, the behavior can become more pattern dependent. So bandwidth is not only a clean frequency domain number. It also depends on the data pattern and run length. So too wide a loop can cause wrong lock or measurement problem. There's another subtle issue. Some data patterns have long spectral lines. Shorter PRBS patterns or periodic data can create side lock. If the CDR capture range is too wide, it may lock to the wrong spectral component. This can create side locking or harmonic locking problem. A narrow loop combined with a proper frequency acquisition loop can avoid this. So measurement can be misleading. If a test instrument uses a very wide clock recovery bandwidth, it may check out low frequency transmitter jitter. Then the measurement eye looks better than it usually is. This is why compliance measurement often define the clock recovery bandwidth. The bandwidth changes with the jitter you use. But in terms of the power and implementation cost, more bandwidth is not free. To increase bandwidth, we may need large charge pump current, faster digital updates, finer PI resolution, low latency logic, stronger clock distribution, or a faster oscillator control path. All of these can cost power and area. In multi-lane series, even a small power increase per lane matters. High bandwidth can also increase switching activity in the PI or DCO update path. So the design goal is not to spend bandwidth everywhere. The better goal is use the minimal bandwidth that meets tracking, JTAL, lag time, and system requirement. So do not make bandwidth too wide or too narrow. But what should we do? Think about the adaptive image for 5 seconds. Correct. Adaptive bandwidth is the practical answer. During acquisition, use high bandwidth, lag faster, track large phase error, track frequency offset. During steady state, reduce bandwidth, lower jitter transfer, lower bandband hunting, lower jitter generation. Avoid tracing, eyesight, and random edge noise. This gives the best of both worlds. High bandwidth when we need speed, low bandwidth when we need a clean sampling clock. This is why real CDR design is not simply high bandwidth or low bandwidth. It's more dependent. Here are the summarized images show you why too much CDR bandwidth can hurt. Because it makes the recovery clock trace noise. It can increase jitter transfer, increase recovery clock jitter, increase band hunting and jitter generation, create jitter peaking, accumulate jitter in retimer chains, fight the equalizer, respond to bad edge information, become pattern dependent, make measurement misleading, increase power, and reduce stability because of loop latency. So, the best CDR bandwidth is not the highest bandwidth. The best CDR bandwidth is the one that tracks useful timing movement and filters harmful timing noise. Again, a good CDR follows the moving eye, but it does not chasing every noisy edge. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and place your comments down below. Lastly, please share the video link with the people who may be benefiting.